Hello and welcome to section 4.7 on applied optimization. In an optimization problem, we are searching for the absolute extrema of a function in the presence of some limiting conditions. Optimization will involve the application of the closed interval method from section 4.2 or either the first or second derivative tests from section 4.4.
Suppose that you owned a large plot of land adjacent to a river and you want to fence off a rectangular field along a straight part of that river. If you are limited in the ability to acquire fencing, say you have the ability to only purchase 2,400 feet of fencing, what are the dimensions of the fence which will enclose the largest area? We can attempt to answer this question by a guess and check method. You can build a 100 by 2,200 foot rectangle and enclose an area of 22,000 square feet. Or you can build a 700 by 1,000 foot rectangle and enclose an area of 700,000 feet. Alternatively, you can do a 1,000 by 400 foot rectangle and enclose an area of 400,000 square feet. The guess and check method is inefficient and most likely will not lead you to a correct answer. But with the techniques we acquired in Chapter 3, we can use derivatives to optimize this problem. There are 6 steps in completing an optimization problem. You begin by understanding the nature of the problem, asking yourself the question, what are you attempting to optimize, and what conditions limit this process? Now, as you answer this question, fix notation to use in your calculations. It may also be helpful to diagram the situation as you fix notation. We are attempting to maximize the area A enclosed by the fence, but we are limited to the amount of fencing, which describes the perimeter of the rectangle which is to be fenced. However, you're only trying to fence 3 sides of the rectangle, as it is unnecessary to fence along the river. We label the rectangle with dimensions x and y. In our third step, we ask the question, what are the constants and variables, and what are the knowns and unknowns? The unknowns are the variables x, y, and a, while the perimeter is constant and known to be 2,400 feet. We now can find the function which is to be optimized. The area of a rectangle is the area of its dimensions, x times y, and we can express the limiting condition p, which is equal to 2,400, as x plus y plus x, the 3 sides of the rectangle we intend to enclose. The function a we wish to optimize has 2 variables, x and y, which are related through the limiting condition p. We can solve for the variable y and substitute it into the function a, and then a will be defined only in terms of x. We will now optimize the function a. That is, we will use the derivative to find the absolute maximum value of a on the closed interval 0 to 1,200. You may ask, why are we working on the closed interval 0 to 1,200? Well, that is the natural constraint that is placed upon the dimension x. The length of the fence cannot be smaller than 0, while it cannot be greater than 1,200 as there are 2 x's and a maximum of 2,400 feet of fencing. The way we will optimize this function is by using the closed interval method
Introduced in section 4.2.
We begin by taking the derivative of a with respect to x. We then find the critical numbers of a prime in the interval 0 to 1,200. As a is a polynomial, the only critical numbers of a are when a prime is equal to 0, that is, when x is equal to 600. The final step of the closed interval method is taking the critical number we found, x equals 600, and the 2 endpoints, 0 and 1,200, and finding which one has the maximum value. When we evaluate a at the values 0, 600, and 1,200, a becomes 0, 720,000, and 0. Therefore, we found the absolute maximum value of a. It happens when x is equal to 600 feet. But we wanted more than just x. We were interested in the dimensions of the rectangle. Recall that we found the relation between y and x, y equals 2,400 minus 2x, using the limiting condition p. So when x is 600 feet, y is 1,200 feet. And this dimension for the rectangle maximizes the area on the interval 0 to 1,200. Let's take a second example. A cylindrical packing tube is to have a volume of 10 meters cubed if the material for the end caps costs $10 per square meter and the material for the tube costs $6 per square meter, What dimensions will minimize the cost of producing the cylindrical tube? Now take a minute to challenge yourself. Pause the video and attempt to minimize the costs in constructing the tube, but be sure to follow the steps outlined in the fence example. As we are working with the cylinder, we have the dimensions r and h, the radius and height respectively, of the cylinder. We are attempting to minimize the cost of the cylinder, but we are limited by the fixed volume 10 meters cubed. The cost of the tube is determined by the material used on the end caps, which are the circles on top and bottom of the cylinder, and the body of the tube, which can be represented by a rectangle. Just imagine cutting the body of the tube height-wise and laying it out flat. We are interested in the total material used for the tube, that is, the area of the two circles and the rectangle. The dimension of each circle is radius r, while the dimension of the rectangle is h by 2 pi r. That is, the height of the tube and the circumference of the circles. Now the volume is fixed at 10 meters cubed, and since we are finding the volume of a cylinder, we have the equation pi r squared times h equals 10. We now need to consider the cost of the tube. We can describe this function by 2 pi r squared times 10, where pi r squared is the area of the end cap, which costs $10 per square meter to construct. And 2 pi r h is the area of the rectangle, which costs $6 per square meter to construct. We can solve for the variable h in our limiting condition, and substitute into the function c,
Then simplify.
We now have expressed c as a function of one variable, the radius r of the cylinder. To optimize, we begin by taking the first derivative. We simplify by factoring 40 and r to the negative 2, and we're left with pi r cubed minus 30. The radius cannot be 0, as the volume would be 0 and not 10. So the only critical number for c is found when the derivative is 0. R is equal to the cubed root of 30 over pi. We need to determine if the cubed root of 30 over pi is an absolute minimum for the cost function. Note that there cannot be negative r values, so the number line starts at 0. Taking the test points 1 and 4 for c prime, we'll find that the cost function is decreasing from 0 to the cubed root of 30 over pi, and increasing after that. Using the first derivative test, this tells us that our value is a local minimum, but as the function was decreasing before and increasing after the cubed root of 30 over pi, it is an absolute minimum. We have the radius, which we plug into the limiting condition relation to find the height. Both values are unsatisfying to look at, but they are the values which will minimize the cost in producing the tube. Though you'll have a pretty tough time creating the tube with a radius cubed root of 30 over pi. In summary, there are 6 steps to follow in setting up an optimization problem. At the end of this list, you must use the techniques of Chapter 3 to find an absolute minimum or maximum for a certain function. Be sure to practice a few problems before class, and don't forget to warm up with WebAssign.
You've seen the basics. Now gain mastery through practice and study.